I'm Richard Hughes, and I'm the Executive Secretary of the Geological Society. And it's my great pleasure to introduce you, or to welcome you, to the third public lecture of 2018, a year which the Society has designated its Year of Resources. And tonight's lecture is entitled Satellite Top Trumps, the Geological Edition. And it's going to be given by tonight's speaker, Charlotte Bishop, of the Society's Geological Remote Sensing Group. Satellites have taken images of the Earth for over 40 years, some designed for specific applications, but nothing has been designed with the end user in mind. Charlotte's presentation is going to take us back to 1972 and to the launch of the Earth Resources Terrain satellite, which became more widely known as Landsat 1, the first of the Landsat series, which is now on its 8th edition. From there, she's going to bring us right up to date to the present day and beyond, into the future, I think, as she takes a look at what's coming up and the benefits that satellite observation brings to Earth sciences. Charlotte's a specialist in remote sensing with over 12 years' experience of working with satellite imagery in a range of sectors, including oil and gas, mining, engineering, and wider environmental applications. She graduated from the University of Reading in 2005 before starting work at Nigel Press Associates Ltd. She undertook an MSc in remote sensing at UCL and Imperial in 2006, where her dissertation focused on hyperspectral mapping over a copper porphyry system, copper mineral deposit in China, using the spaceborne Hyperion satellite. She returned to Nigel Press Associates as a remote sensing specialist and project manager, focusing predominantly on optical satellite systems. In May 2017, she was appointed Technical Business Development Lead for Terrabotics Ltd, a tech startup focused on developing and deploying algorithms developed using computer vision and artificial intelligence to process and analyse satellite imagery. She's been an associate editor for the International Journal of Applied Earth Observation and Geoinformation, which produced in 2018 a geological remote sensing special issue, Impress, for which she was chief guest editor. And since 2017, she's been serving as the first female chairman of our remote sensing group. So, ladies and gentlemen, please welcome Charlotte to the lectern.
Thank you, Richard, and hello, everyone. Thank you to the Geological Society for inviting me to present today. Just to add a little bit to what Richard was saying, and to give a bit of background to the remote sensing group of the Geological Society. We're a group of volunteers, essentially. A couple of my colleagues are also here in the audience watching this afternoon. They're hiding in the back corner, so and hopefully won't be asking any particular questions later. But we're a group that was set up specifically to bring together those in the industry who were geologists or who had an enthusiasm to use the wealth of satellite data that we now have available. The group was set up in 1989, and we're an extremely active and international group, and we host a conference every year that has now kind of gone to an international home and away type situation where we hold 1 year in London and 1 year in another city. For a big 3-day conference on geological applications using remote sensing, but not just satellites. We're only going to talk about satellites today, but remote sensing covers a much wider remit than that. So without any further ado, I will we'll start going through, and how this is structured is I'm going to go through some fundamentals of remote sensing. We're going to go through a bit of a timeline, focusing on some of those key missions, and then we're going to look at some of those applications, and then I'll close out with some final thoughts on what's happening in the future. So I'm not going to read what's on the slide. I'm sure you can do so. But remote sensing, really, to break this down, is essentially what we can see without touching. And that can be me looking at the people in the audience, as I am. It can be from a surveying point of view, if we're taking a picture, for example. It's exactly the same concept. All we're doing is taking a picture from space instead, in this case. As I mentioned, remote sensing is a very broad subject. It also covers aerial data and ground-based remote systems. So it really is a very vast subject, which is not at all what I thought when I first got into this. So when people ask me what I do, and I say, I interpret satellite data, this is what they often think. They're like, oh, you do something with the weather, which I don't do anything with the weather. But this is a satellite image, obviously. But these types of satellites are taking global pictures and daily, regular updates of pictures, because that's exactly how we need to view the weather systems and understand that context. For what we need for geology, this data is not going to be useful to us. And I'll explain what the difference is a little bit later. They also say, oh, well, if you don't work for weather satellites, you must work for Google or you must work for TomTom. I don't do that either. But a lot of people will have probably used Google Earth. And Google Earth is a fantastic tool, but there is so much more that we can do. Google Earth has really kind of opened the wider kind of public view of imaging, and allows us to zoom in not just on our house, but on maybe holiday destinations and other things. But us in the industry, we also use Google Earth as a fantastic tool to do a quick check on an area or understand a little bit more of the context, where perhaps we've only been sent a tiny little area to look at, and we need to understand what's happening around it. So before I go any further, just a quick show of hands. How many people have used satellite data, excluding Google Earth at this stage, in the past? Okay, wow, I actually think there was more at the 3 o'clock presentation who had. So, okay, well, it will be quite as straightforward as I can make it, and there'll be lots of examples, lots of pictures. So I hope for those who do know a bit, this is merely a reminder, perhaps, than anything else. So this is what we're talking about. We're talking about top trumps. So this is, I actually have these here. I'd be happy. I only have one copy, I'm afraid. They are a very rare edition, it seems. But the Institute of Environmental Analytics, based in Reading, produced these off a kind of intern-based project that they were doing last year. And I picked these up at a conference, and I just thought this was a fantastic idea for a talk. So I'm not going to go through all of the satellites, and I'm not going to go through the advantages and disadvantages in that way, because you'll understand, I hope, quite quickly that it doesn't really work like that when we talk about satellites. But there will be facts, and there will be figures, and there will be, if we have time, a quick quiz at the end as well. So just to put this into context and give us a little bit of an understanding of how far away these satellites are, we've got this nice graphic that was developed as part of the geology. I'm not expecting you to read this, but to kind of break this down a little bit further, this is a nice little map of where we are. We're obviously here in London, in Piccadilly. The International Space Station, which obviously has a number of cosmonauts and astronauts, but also lots of scientific instruments on it as well, is about the distance from here to Paris into space, about 400 or so kilometers. In contrast, the satellites that we're going to talk about today, so we're not talking about GPS satellites or anything, we're just talking about the Earth observation, so the mapping type satellites. They're about from here to Glasgow. And the weather satellites that we talked about, I didn't really have a slide big enough to depict this, but this is all the way to Sydney and back again. This is how far away they are. So, I mean, 700 kilometers is still quite a long way, but when we start talking about, 36,000 kilometers, then that puts it into an entirely different ballpark. So we won't be talking about weather satellites today. But space is quite busy, and it's getting increasingly busy because space is becoming very cheap to get into. There's lots of companies now that are launching small satellites, and we'll talk about a number of them later. This is a kind of pretty comprehensive picture of most of the satellites that we might use or have used in geological applications. You'll probably be pleased to know I'm not going to talk about all of these this evening, because we might not make it to wine by 7. So we're gonna focus on really the key milestones in our industry, in geology, that also kind of work wider as well, because a lot of these satellites, they haven't been built specifically for end users, but they are therefore multi-purpose. So how can we use those to our benefit? So we're going to just go through a bit of the fundamentals, and the reason for doing this is that it will then help to set the scene for when we go through the timeline to help understand what the value is of those different key milestones that I've selected. So there are several considerations when we, as remote sensors, are working with people to understand what they want to get from satellite data, and therefore what satellite might be the most suitable for them for that purpose. What level of detail do we need? Do we need to cover a very small area? Do we need a big area? Do we need to repeat this study? All these kind of things have an impact maybe on the type of option we go for, and of course, how much budget do we have? And that then leads into some of these considerations that we're going to go into in a little bit more detail. I'm going to cover not all of these, but the spatial and spectral resolution and the type of satellite, just to give you an indication as we lead into the timeline. Now, I've just realised I have forgotten to change something on the next slide, which was incorrect in the last talk. So bear with me, as the arrow is the wrong way round. This arrow should be that way, but the rest of it is correct. So what this is showing is the trade-offs. So typically, if we have a satellite that has a very high coverage, so covering a very large area in one snapshot, it is typically low cost and at low resolution, and I'll explain what that means in just the next few slides. And vice versa, if we talk about high resolution satellites, they tend to be higher cost, but smaller area of coverage. So it's kind of more like a graph like this as we go through. I'm not going to talk particularly about cost. If someone wants to know something more on that, I can talk about that afterwards. So spatial resolution. This is the highest resolution satellite in space. It's 25 centimeters, but it doesn't look at the Earth. This 25 centimeter satellite has been taking pictures of Mars for over 10 years, and we haven't had the equivalent on Earth until 4 years ago, and still it's only 30 centimeters. Because of US restrictions largely, but I'll touch on that a little bit later as to some of the other implications of that. So this sensor, which is called HiRISE, the High Resolution Imaging Science Experiment, was launched as part of the Mars Reconnaissance Orbiter sorry, not 2008, it's actually older than 10 years. This was launched in 2005, reached Mars in 2006, and has been taking pictures ever since. This data is free. This data, you can go onto the website, you can download the data. There's tools as well that can be used to analyze this data, so everyone has the capability to play around with what is a really high quality data set and look at some of the fantastic features for geology, but also other things on Mars. But if we kind of break this down a little bit more, and this is a simulation just to kind of give a bit of an idea. So when we talk about low spatial resolution, we're talking about higher numbers. So a low spatial resolution means less detail. So if the pixel is bigger in size, we're not going to be able to see as much clarity as if it was, the other way around. So a 30-meter pixel size, so 30 meter by 30 meter, we get it often, it doesn't give us very much detail. It's very good if we start to move away from that and look at larger context, but if we're zooming in on an area, it's not going to give us much detail. As we go through to 10 meter and 5 meter, we start to see a bit more detail, but we still haven't got perhaps all the crisp detail we might need if we're doing perhaps access mapping or something like that. As we go to half-meter resolution, we can see this is a mine site quite clearly. These are the benches going into this mine in northern Australia. And we can see buildings, we can see trees, we can see things. This is from space, a half-meter resolution. And so just to give a kind of context, so when we're talking about satellites later in the timeline, high resolution is half-meter or anything from 1 meter lower, as it were. Whereas when we're talking about low-resolution satellites, we're typically talking about anything that's maybe 10, 15 meters and above. So then, on opposite, we have the spatial resolution side. We also have the spectral resolution side. Now, this slide may look complicated, but it doesn't need to be. If we kind of break it down and take a step back. What we can see with our eyes is red, green, and blue. This is what is visually available to us. But outside of that, there's obviously a lot of other things going on. We have a lot of other color that we can tap into. We can't see it, but it doesn't mean that we can't image it, because we know that there are infrared cameras out there. It's exactly the same concept. So we can make the most of the bits that we can't see and actually optimize those to extract the features that we want to. Every single feature that we have on the land surface has a spectral signature. This is what these are called, these coloured lines. This is a signature of a particular feature. It's not necessarily completely unique. It may be very difficult to distinguish between some of those things. But from a geological point of view, this is the bit we're really interested in. We can see very clear features, particularly in this part of what we call the electromagnetic spectrum. We might only be able to see this, but we can image and map this very clearly. So to kind of put that into context, just got a couple of colour visualizations to make that a bit more obvious. So this is a natural colour image of the Flinders Range in Australia. This is exactly as we'd see probably in Google Earth. It would look very similar to this, but it's like an aerial photo in essence. If we start to alter the colours that are going into that red, green and blue component by expanding that out to the infrared, we're starting to see a little bit more detail. So you might have noticed that the vegetation's turned from green to red. The reason that that's quite powerful is that the infrared has a very, very strong signature of vegetation in red. So we can actually start to separate that surface feature from some of the others that are in the scene. If we go a little bit further and start to bring in some of those longer ones, those areas of the electromagnetic spectrum that are very specific to geology, we can actually identify even more features. All of these different colours that you see here are representing different types of lithology. So it becomes a very powerful tool. And what we do all the time for projects is take the area that we're looking at and put it into context by understanding the visualization before we do anything else. And perhaps in some stages that may be all that's needed as part of the work, and it may be that there's then further interpretation that's needed. And we'll show you some examples of how that's used and how we can actually map from this data a little bit later. But there are many areas of the world that are quite problematic for us with satellites because they're cloudy. We have a lot of tropical areas. UK, for example, also has a lot of cloud. It's not very tropical, but it does have a lot of cloud. So this becomes a problem. We can't see through cloud. It's a satellite. It's no different than having something else that's a blocker. We're even within the kind of infrared portion of the spectrum, we can't penetrate those clouds until we go much further into the microwave. And I don't mean the thing that's in your kitchen. But what we can do, there are other satellites that have that capability, that are active sensors that are sending and receiving a pulse. So an optical sensor it has to work in daylight. It's reliant on the sunlight to be able to capture a picture, just like you would if you were taking a picture with a camera. With radar, it has its own signal. This is exactly the same area, but all of a sudden we can actually see what's going on underneath, because radar can penetrate the clouds. It's an active signal, which means it's sending and receiving its own signal, therefore it's not obstructed by the clouds, and we can start to see features that we otherwise wouldn't be able to map if we were just looking at optical data. Now, this doesn't mean that one is better than the other in, if it's a tropical area, I must use radar data, because it still may not be appropriate. It could be that there's a combination of the two that might be a better way forward. So it's not necessarily a trade-off between one or the other. It may be a compromise of a combination. But this data, and we'll go through some of the examples here a little bit later, is very useful for geological mapping. As you can see, it kind of looks like it's highlighting some of those features, even to the untrained eye. But we can also use this data to map ground motion. We can also use this data to map oil slicks. And these are applications that are not possible with using the optical satellite data sets. There are many fewer of these in space than there are optical sensors because of the capacity and the requirements that they need to have to operate, but they are still extremely useful as sensors for us in the industry. So now we've gone through the fundamentals, so you guys all know how it all works. So we're gonna go to 1972, and we've got maybe 7 or 8 different timestamps, so we're going to look at some of those key milestones in geological remote sensing. So 1972, and hopefully if you were all listening, a satellite called ERTS, Earth Resources Technology Satellite 1 was launched. This was a kind of 80-meter colour sensor, so spectral bands, as we've been talking about. And this was its first image. 2 days after launch, it took this image of Dallas in Texas. As you can see, the red features here are vegetation, so we're already using the capability of playing around with those colour channels to highlight different features. But they decided that name wasn't very good. I don't know why particularly, but a couple of years after launch, they renamed it to Landsat. And Landsat is something that we, as geologists, geological remote sensors, would probably say is our mainstay for mapping and has been for all of that time. Companies have been set up based on the launch of Landsat 1. People started interpreting even from this lower, coarser resolution 80-meter data. Since 1985, it's had 30-meter pixels, and that has stayed the same from that launch up until today. And we're now on Landsat 8, with only Landsat 6 being the only one that failed, but we just don't talk about that one. But Landsat 5, which was launched in 1985, has an extra kind of fact to it in that it is the longest serving Earth observation satellite. It was operational for 27 years. Collecting imagery nominally every 16 days. They did shut the power down for a while because they launched another satellite, and then unfortunately there was a problem with it. So they had to turn it back on again and continue collecting. So that ended its collection just a couple of years ago now. But it does hold that record, and I think it'll be very difficult to beat that based on how the systems are changing and working now. So the next milestone, I know it seems like quite a long way away, a lot did happen in those 20 years, but actually it was still very much on the optical side, and didn't really provide significant improvements to the resolution, at least from 1985 onwards. So the next real milestone was 1991 with the launch of ERS-1, so the European remote sensing satellite. So this was a radar satellite. They only made it as a radar. They didn't have any optical. It was the first operational radar in space. There were some that were earlier that were used more for kind of scientific missions, but this was the first one that was available more commercially. It was then followed a couple of years later by an identical satellite called Earth Resources Satellite 2, which it did exactly the same thing. And then there have been subsequently others in the series, but not of the same type as this particular one. So it wasn't, until the launch of this satellite, we hadn't even considered some of the applications of radar. We'd started, in the late 70s to look at some of the applications of using this for mapping pollution slicks on the sea, but it was not really being done operationally. Understanding that was still quite difficult. And it was the launch of this that really gave the capability. The resolution was optimal to be able to do that in a different way than done previously. So 1997 would have been the next milestone, and we'll look at why that wasn't the case. So 1997 was the launch of Early Bird 1, which was going to be the first high-resolution satellite into space, 3-meter resolution, a real game changer to go from a 20-meter resolution satellite, which was the best at the time, down to 3 meters, and it was dubbed the first civilian spy satellite by the New York Times the day after launch. Unfortunately, 3 days after that, they lost contact with it, and it never actually was able to collect any pictures. So unfortunately, there was no backup plan. The private company that launched the satellite weren't able to recover, and it was scrubbed from the memories of, I'm sure, the people at Earthwatch who'd launched the satellite originally. But a couple of years later, in 1999, another US company decided to launch a satellite called Iconos. This was going to be 1 meter, so even better than the 3 meter. It really pushing those boundaries when it comes to the spy satellite side of things. But unfortunately, they followed a similar fate because their satellite also blew up on launch. However, the bonus that they had was they had a backup. So they had Iconos 2, which was identical to Iconos 1, in a warehouse that they were able 6 months later to put into space, and it then became Iconos as we know it today. So yes, space is not always a very easy thing to get into, and certainly wasn't then, and we still see some of those things that do happen, unfortunate incidents now with launches. And this was the first image that was taken with Iconos. So this is a 1 meter. It was actually collected at 80 centimeters, but the US government at the time had a restriction because this data was also used for military applications. They couldn't release the data at any higher resolution. But we could start to see road markings and cars. I apologize, the quality of this image is not very high. But we're seeing a completely different view than we previously had of the Earth. And you know, these small sensors were actually really powerful in terms of the quality. Also in that same year, we had, it's not actually a satellite, it's a sensor on a satellite called ASTA, but the reason for including it is its significant importance for geological applications. So ASTA provided, I guess, a step change to what was already being provided by Landsat. Landsat had the capability to map clays, but very broadly. As well as other iron minerals and other materials, whereas ASTA had significantly more spectral capability, so much more opportunity to discriminate some of these features. And not just in the infrared, they also had spectral capability in the thermal. This was the first satellite that had that capability. It's still operational today, not fully operational, there are some issues, but it is still working even after nearly 20 years. And then 2000 came with the launch of a satellite called Earth Observing 1, which had a sensor on it called Hyperion. I couldn't do a nice pretty picture in the same way I could for the other ones, mainly because the scene size is so small for this data, it would have looked very, very pixelated. So this was a trade-off. This was the first, it was a science experiment, it was designed as a demonstration. But it was a trade-off between optimizing the number of spectral bands to be able to discriminate these materials, but they had to trade off by having a lower resolution, spatial resolution. And this is because of the capabilities of optics, basically. And understanding how the interaction of those signals work means that they could only work within those restrictions. But this scene, so this is a 30-meter pixel scene size, but only over 7.5 kilometers of width. In comparison, a 30-meter of Landsat covers 180 kilometers. So this is a tiny, tiny strip of data that's collected. The example here, I rather cheekily stole from my own master's project. This is in China, in the foothills of the Himalayas. And what I've done here is extract some of the different types of minerals that are present here, some of the alteration patterns. So this is what I've extracted from the image. As you'll see, it's quite noisy. And then I've compared the spectral signatures directly with ones that are kind of known laboratory spectra. The reason we're kind of showing this is that if we had a Landsat image of the same thing, for example, we'd get a very blocky response here. We wouldn't be able to detect some of the very subtle changes. The Hyperion, obviously being quite noisy, still makes that very difficult, but we're actually seeing a lot more of the picture than we would otherwise. And this was the first hyperspectral satellite in space that had this capability. It is still operational, and all the data is free, as is all of the USGS data. 2007, there was a number of launches. I'm only going to focus on a couple, really. The reason for that is Cosmic SkyMed is a radar satellite, so not dissimilar to ERS, but the reason that it has value in being included here is that the way a radar system works, as I mentioned, it's sending a pulse and receiving it. This was the first one that had a slightly different wavelength, a slightly shorter wavelength. And what that means from a kind of geological point of view is that we get a little bit more understanding of the texture of the ground. We're not seeing spectra with radar. What we get from our response is the response of that signal to whatever's on the surface. So we're looking at texture rather than color, basically. So Cosmic SkyMed and TerraSRX, they were both launched, two different companies were launched in the same year, and both have very similar specifications. We also then had the first half-meter resolution satellite that year. And this is a panchromatic, so black and white only had the one single band. It was supposed to be color, but they wanted to launch it quickly to have that crown as being the first ones in space at the moment. At that time, there was quite a lot of competition. The space race in the US commercial side was quite high. So Worldview 1 was launched at half-meter resolution, and this is a high-resolution image over Addis Ababa in Ethiopia, and we can see the level of detail that we're getting from a satellite, which is quite mind-blowing, really. 2 more years left, and then we get to see some nice application pictures. So 2013. 2013 was a bit of a game changer for a number of reasons. And in fact, the 2 examples I'm going to show, they now are actually owned by the same company, but they both have very specific value more to remote sensing as a whole, I think, than maybe specifically to geology, but I think that it was valuable to include them. So just need Gary to start the video. So in 2013, the first satellite was launched into space that had the capability to capture high-definition video. So this was is still collecting, 1 meter video at a rate of about 30 seconds, a 30-second frame rate over about a 90-second kind of video sequence. It's a kind of targeted, it's not on all the time. The capacity of the satellite is not going to make that possible, unfortunately. But the intention for this was, I think, largely surveillance. I think we're still really finding out what the application for video data is, to be honest. But what it is a fantastic demonstration of what can be done from space, and this will only change and improve as we go forward. And there are now 3 or 4 of these satellites in space and capturing. I'm not sure if they're capturing video as regularly, but they're certainly taking pictures at high resolution. So I think if we can. But from my perspective, from geology, but also from my job, which isn't just the GRSG, is at Terrabotics, is we take data and we're processing high-resolution, high-accuracy elevation models. The value of video sequences to us is that the more images that we have to go into that process, the more we're able to resolve some of the difficulties we have where we have lots of shadowing. For example, if we see here in the mine pit, if we only have 2 images and we want to make an elevation model, so we're basically looking at the differences in the angles to understand what that topographic component is to extract an elevation model, then we're going to miss some of those areas. We're going to get shadows, we're going to get voids in the data, which isn't going to be very useful to us and probably to the client. So if we have multiple images, and a video is fantastic for that, but it could also be a multiple framed single collection, we can resolve some of those issues and actually come out with a much cleaner elevation product. The same company, although they weren't at the time, also had launched a series of these doves, and I don't know if anyone has heard of Planet Labs, other than the people who I know will have heard of Planet Labs. But Planet, it's now known as Planet, but Planet Labs was a NASA group of scientists who decided to launch these tiny satellites for about $60,000 into space. Now these are the size of a shoebox, and they are collecting images at 3 to 5 meters of spatial resolution. So, what we would term a high to medium resolution. So, a fantastic level of detail from a satellite the size of a tiny shoebox. And this is important from a geological point of view because we're actually getting monitoring. So this example here, this is actually a case study on our website at the moment, which is thank you to Planet to providing, where they were using this data to monitor glacier movement. The value of this is that there are over 150 of these tiny shoeboxes in space. So being able to capture an image very regularly is a perfect application for something like this. So if you're looking at geohazards and other kind of monitoring oversight where that kind of larger area doesn't have to necessarily be too detailed, this could be a good solution. And there are many more of these types of constellations being launched that have some similar capabilities, but perhaps provide some other advantages as well. So 2014 is our last stop on our timeline. And we're ending with another Worldview satellite. There isn't a problem with Worldview 2 that did launch, that is operational, it is all fine. But Worldview 3, from a geological perspective, is much more interesting. And the reason for that is that we talked about ASTA a little bit earlier and its capability to distinguish many more, say, geological features, minerals, than we could previously. Worldview 3 is very similar to ASTA, but at significantly higher resolution. So all of a sudden, we can see a complete step change in the level of detail that we can map. And we'll see an example of exactly how that works and what that really means in a slide or two's time. Not only that, but it is also the highest resolution satellite in space. This is a 30 centimeter pixel size satellite. At the moment, as I mentioned previously, the US restrictions have limited in the past the maximum resolution that is available to everyone globally, apart from to the military. That was the same with this. They actually lowered the restriction to allow this satellite to be used commercially, at least part of the restriction. There are still some other restrictions on this data, but certainly the 30 centimeter color data, like the lovely image you see on the screen, is something that is available to purchase. Their restriction now is down to 25 centimeters, and I'm sure there'll be satellites that come along that either meet that and or challenge that going forward. But at the moment, this is what we're working with. But in comparison, we've had 12 years of 25 centimeters on Mars, but whatever. So that's all great. We've done the fundamentals. We've understand a little bit about some of the satellites that are up there. What can we do with it? Where do we start with this? Okay, so geological interpretation seems like a logical place to start. Let's start with elevation models. And I touched on this briefly when we were just talking about the video. But what we're also able to do is take this at different scales as well. So we looked at high resolution from video and the kind of elevation model we saw there. We can also do this at much wider areas, at lower resolution. So same principle, spatial resolution. Low resolution means less detail. This is an area of southern, I've completely forgotten where, southern Israel, and there is an airstrip here. Not that you can see it in this particular resolution data. This is a data set that was captured across an 11-day mission of one of the shuttles called SRTM, Shuttle Radar Topography Mission. This is a 30-meter grid. And then this is a 2-meter gridded elevation model that I extracted a couple of weeks ago and thought would be quite a good comparison to show. And automatically we can see some access routes. We can't actually see the airstrip, it is slightly further up, but we can see some buildings and other features here. It doesn't necessarily mean that the high resolution is better than the low resolution. Again, it comes down to what we need to use the data for. But certainly if we're looking for clarity on particular features, then perhaps the elevation model at the higher resolution is the one we need to use. And we can use this type of data for lots of things. It doesn't get used independently of other data. Often it is combined together because the combination is really the power that we have in terms of what we can interpret. So we can look at slope, which will give us the kind of angles of access. Can we get over a particular feature? We do a lot of work in, say, seismic planning and accessibility, where people need to understand, can they get a truck over a particular area or not? We can also shade it. We can make it look nice visually. We can understand a little bit more about the context, and we can then put all that together with an image and really add some color to that. And then just a couple of examples. So a number of the next slides will have logos and copyright statements from companies who are corporate members of the GRSG and have kindly provided their case studies and examples for us to include in this. So my thanks to them. And what we have here on the left is a range of different shaded models. So these are elevation models where we've looked at different illumination conditions and displayed those. They may look very subtly, they may look actually quite similar, but they are subtly different. And the value of doing this from a geological perspective is that if we can visualize the terrain all around in terms of the illumination, we can get a much better idea of some of the very subtle structural changes. Lineament changes is what we're kind of focusing on. So these are structures that are on the surface, but that can give us an indication of what might be going on under the surface in terms of faulting, perhaps, and other features. And then this is the type of features that they can extract. This is an automated algorithm that they have in their software, but this type of feature can also be manually interpreted, and there are many people that are geological consultants who do this type of work. And in fact, there's a nice segue into this example, which is provided from another of our corporate members. So they've used topographic information, so elevation models, as we've just looked at, also imagery, and this might be optical, might be radar, maybe it's a combination, I don't know. This is an area in North Iraq where they have all of this is interpreted from satellite. This is not interpreted from field surveys. While they may then have used that data to verify what they're seeing, but all of this is interpreted from satellite. I can assure you, to those that know what they're looking at, this is relatively straightforward to do and to understand. So they can identify the different lithologies by optimizing the visualization, as we've mentioned. And then they can also look at the structures and the impact that has. And that can give an indication of perhaps what might be happening under the surface with regards to mineralogy, circulation of fluids, oil, gas, all those kind of things. So this is where this type of information is used quite a lot across the industry, both from research and commercial. And this is just another nice example. This is from the East African Rift. So we're taking a much bigger view out here. We're not looking very detailed, but the same kind of concept in terms of bringing data together. We touched on lithological mapping. So once we have the capability to separate the different types of materials, at least to a degree, this isn't going to have all of the answers. I'm certainly not suggesting a satellite replaces any of the lovely field work that geologists like doing and is really vital to help verify what we see on a satellite image. However, it's a great tool to provide that context and reconnaissance, and particularly in areas that are very remote, perhaps very difficult to access. So if we touch a little bit more on mineral mapping, this is a nice comparison between ASTA and WorldView3. As I mentioned, there is a kind of step change difference in terms of the level of clarity, but overall the sensors are relatively similar. But neither of these were designed specifically for geology. ASTA perhaps was more focused on geology than WorldView3, but WorldView3 was very much more focused on military applications. So this is an ASTA image. We're in the southeast of Spain now. We're looking at a gold mining area called Roda, which has been mined for a number of years, and you can actually walk around it, but there's still quite a lot of surface alteration here. We've just run, or our colleagues at ITC have run an ASTA clay ratio on this. Ignore the coastline. This is an artifact in the data, which is very common. But what we're focused on here is the red points being the high, strong ALOH, which in this case is essentially clay content. So it's a bit noisy, doesn't really tell us very much. You know, if we looked at a bigger picture and looked at some structure, that would give us some indication. Believe me, it would. It may not seem like it does. However, if we look at WorldView3, same area, we can see more visual detail. We can already kind of map roads and features that we couldn't before. This is exactly the same ratio that's applied to WorldView3, and we get significantly improved detail. So again, it doesn't necessarily mean that one is better than the other. It depends what we want to do. ASTA data is free. This data is definitely not free. So there's also that kind of component where perhaps we might need to trade off. Maybe we do a larger study and then focus in, or there are lots of considerations that we might need to look at. But what that does provide is a really great opportunity to add more value to our interpretation than perhaps we had previously. We can also do oil slick mapping. I touched on this previously. I'm not going to go through necessarily all of the mechanics of how that works. However, in essence, we have an oil seeping from the seabed. We cannot see the seabed. We can't see subsurface, as I've mentioned. But what we can see is its expression on the surface. What that means for us when we come to interpreting the data is that on a radar data set, so we're going back to radar now, and I'll show you why optical is not very useful for this. On a radar, as oil reaches the surface, it changes the sea surface in comparison to what's around it. So if you remember, a radar is an active sensor. We're sending and receiving a pulse. It's reacting to what it sees on the ground, what it's interacting with. In this case, it's interacting with the sea surface, and we're getting a very kind of speckly grey response. It hits the oil slick, nothing. So we're not getting that return signal because it's essentially a sheen on the water, and it's dampened down those waves to make it look completely different to what is around it. So what this means is we can map oil slicks. We can also, it can be confused. There are lots of other factors that come into doing this effectively. So it isn't necessarily a case of just picking up a radar image and, I can map some oil slicks. But in principle, that is, this is what we use radar data for. And this has been done for the last 25 years or so. It's been done since about the early 90s and only a couple of years after the launch of VRS. So what we're looking here is pollution slicks. So there's a ship at one end of this arrow, I can't remember where, and this is the oil plume that's come from it. So we can see natural seepage slicks. So companies often want to understand this kind of information as part of assessing whether they perhaps procure a new license block. They want to understand if there's any impact or pollution that's happening around their rigs. So there's a lot of applications for this type of data. This is what a portion of the Gulf of Mexico looks like. It is quite a seepy place. I'm told that's a technical term. And that's because there are a lot of oil rigs here. There is a huge amount of oil in the Gulf of Mexico, and we've been monitoring that. Companies like MPA Satellite Mapping have been monitoring that for, as I say, for over 20 years, and they have extensive archives of these areas and others like them. I mentioned to you before that radar can see through clouds, which it can. However, rain does have an impact on the sea surface. So it's going to disturb the surface in not dissimilar way to how oil does. So we do get disturbance from rain, even if we can see through the clouds. So it doesn't always happen, and not every cloud obviously leads to rain, but it's something else that we have to factor into our interpretations at time. But on this optical image was taken just an hour after the previous image. Of course, we have clouds. We also have issues when we're looking at oil slicks on the sea surface with optical data. Because of the sun elevation, it can make it very, very difficult to see those clearly. On the radar, we don't have that same issue because we're not reliant on the sun to image, and we can image day and night. We're much more flexible with a radar system. So it becomes a real key tool for this type of mapping. Now, I'm definitely not going to go into a lot of detail on the fundamentals of how this next process works, which is a process called INSAR, Interferometry Synthetic Aperture Radar. Don't worry, there's definitely not a test on that. However, it is something I can provide some more information on if someone is interested based on the examples. Come and see me afterwards. So ground motion monitoring. Yes, we can monitor ground motion from satellite, and I'm going to show you some examples of how we do this. This is a pub. I haven't skewed the picture. It does look like this. It's near Birmingham, I found out earlier, and it's called the Crooked House. So it's quite a nice way to lead into the next couple of slides. So there are many different applications for this type of technology. It's used extensively, and I've only got two examples here. One which is over a coal site. So we're in South Wales at the moment, and we're looking at this particular area here, but all this whole rim here is all old coal mining sites. So what we're looking at is trying to understand how that area has moved from a satellite. In very, very quickly, how that works is a radar signal is sent and received. We've talked about that. If we can then take the same image from a radar satellite a few days later, or the next time that satellite passes exactly that same point, and we're sending and receiving that signal, we can understand the time difference of that signal, which can then equate to the elevation difference. I can explain that in clearer terms later, but just to give you a bit of context on how that process works. And what we can map, you see these points here, this is based on features that the radar is able to get a consistent response from. We can actually map some of those changes. So we're looking at, this is in millimeters, 30 to 30, so red being subsidence, blue being uplift. So some of this will be expected. We get natural movement, particularly over mine sites, you'd expect so. You're doing excavation as well as perhaps piling of materials as well. The green areas being stable, but we're seeing quite a lot of red over here, which is probably related to either some further excavation or some slumping over the area. This is a very nice example from CGG, which is showing pre and kind of during construction for Crossrail. So I thought this was quite a good one to include. So green is stable, exactly the same colour scheme as we saw in the previous slide from the other company. Red being subsidence, Blue, we don't really have very much of that on here, but so London is built on clay. Clay moves, this happens, it's very changeable due to the seasons. We have a very wet summer, we have a very dry summer, it has a significant impact. We're going to see these small changes anyway. The power of this is to help to monitor where there's perhaps something that's a little bit more unexpected or something that has some value in understanding any potential impact and wider impact than maybe we can do with just a standard ground survey. So this is the Olympic Park over here. I'm just going to turn on the cross-rail route so that it's obvious. But what we see here, we can see these little red patches. I'm just going to skip on to the next slide. Now, all of this is expected. I don't want anyone to go away from this lecture thinking that, oh my goodness me, Tottenham Court Road is sinking, because it's not. These are all things that have been totally accounted for as part of the engineering process. But what people want to understand and monitor is how that's changing. Is that happening at the rate that was expected? Is it something that perhaps they need to look at? Or is it being consistent with what they were thinking would probably happen? So in comparison, we've got Bond Street, so number 1, 2, and 3. Oh, hang on. So Lambeth being down here is very green because there's not a lot happening down there. In comparison, we've got these red areas, which are the hotspots where there's been very deep excavation around those stations to help support the cross-rail network. So this is a very easy way to take a very big view, understand what's going on in the wider context that helps absolutely support what's going on the ground, certainly not designed to replace those features. So last two examples, volumetric analysis. So from what we do, one of the things that we do at Terrabotics is we take this high accuracy elevation data sets that we work with, and we repeat those over particular areas. So if we're looking at a mine site, there are opportunities to map the changes. So we can visually see there's been a lot of changes over a mine site, whether it's the tailings, whether it's stockpiles, whether it's maybe inside the pit to a certain degree, but we want to be able to quantify that. So one of the ways that we can do that with high quality data, of which we now have a lot of, we can actually start to, with a reasonably very high precision, where we have a good ground control and survey network, we can get vertical accuracies of 25, maybe 30 centimeters if that data is provided. And actually provide some indication of the volume of these stockpiles that might not necessarily be of interest just from a commercial point of view for a mine, but also for understanding if there's any implications of that. Where they've expanded some of these tailings, does that potentially pose a risk? Are there other considerations that they need to understand? A lot of mine sites have regulations that they mean that they have to report on the volume of this material, but actually some of the more traditional surveys are extremely expensive and perhaps difficult to fly because they're often involve in aircraft and therefore permits. So if they can use this data to infill some of the more detailed surveys, then this provides a different advantage. But we can also see other features. We can see changes in infrastructure. We can even see trucks and other features that are happening, things that are happening in the pit. So we can start to understand, is this what was expected? Some of the people that are looking at these mines, they may not be based on the mine site themselves. They may not necessarily know what's going on day to day. So this type of data is one easy way to provide a quick snapshot, maybe once a week, maybe once a month, whatever that might be. And we have the capability now to be a lot more flexible on those timeframes. But also, stepping slightly away from geology, but certainly very related, planning and environment. A lot of the projects that require geology, engineering, mining, you've got to understand how to, the access into those areas, perhaps the land cover, all of those elements are still important. And we can use satellite data to help with that as well. This is some work that we've been doing in the southwest of England, understanding land cover change as part of a mining company's kind of remit to see the access, but also we've got a lot of agriculture in the UK, as we all know. So if we can map the differences between the vegetation types and grouping, understand perhaps any seasonal impacts, then they're much better informed to make the decisions that they need to for that next planning stage. And then we can bring all those things together. They can be visualized. either like this or as separate layers, and then combined with other data that, that users have as well, to really provide as much value as possible. Because there's no point in providing an image to someone for it to then go and sit on a hard disk somewhere, which does happen more times than it really should. If you can bring that together with other data and really show the value of how those things link together, that's where people really understand the value of this type of data. So, we don't really have time for the quiz. I'm going to skip through my slight quiz, but we'll do it quickly. We'll do it quickly. So we're just going to go back through the recap of the milestones. So 1972, Landsat, this was really the kind of key for geology that really started things. A lot of companies, as I say, were built on that, and it really did start the process for us using this data more operationally. 1991, we had the ERS. Unfortunately, I don't have a top trump card for all of these satellites, but Iconos, so this is what Iconos looks like. Terra, so this is where Asta sits on. Hyperion. We had Cosmo. We had, that was TerraSAR-X. We didn't talk about that one anyway. And Worldview 1. Then we had Skybox, so this is the one that's capturing video. So this is a box that's only a few meters wide, square, that's capturing video data. And Planet, and these are these shoebox-sized satellites, and these solar panels kind of fold out as soon as they get into space. So, you know, it's amazing the technology that goes on something so tiny. And 2014 with Worldview, and we're kind of up to the present day. That's not to say that things haven't been happening since then. There are lots of things that are happening. For me, those were the key milestones that I believe are relevant to geology. When it comes to the future, your guess is as good as mine to a certain degree, because I don't have a crystal ball. I don't know exactly what's going to happen. But what I do know is that it's clear we're seeing a lot more smaller companies launching satellites, really pushing the bounds of technological capabilities, whether it's from the Planet Labs in boxes, whether it's video from space, whether it's changing the way we're imaging the Earth, and combining sensors together in perhaps a much more optimal way. There are lots of things in the pipeline that perhaps follow suit of what we've seen in the past. And the reason for this is that there's extensive value in the continuity of those archives. With Landsat, we have the capability at 30 meters to go back to 1985, which is a ridiculous amount of data to work with, but a fantastic opportunity for some of those longer historical assessments that we may need to do on occasion. And to have that reference is fantastic. If we then move to the radar data set, some of those nice ground motion maps that we looked at, they are reliant on having big archives of data. So the more continuity of those systems we have, the better. Also, I think that there will be a step change in terms of the users themselves having much more impact. It won't just come down to the technologists building the satellites and thinking, yeah, it's really cool, I've got a satellite, which is great. But ultimately, there has been a problem in the past where these satellites are built and it's very little understanding maybe as to how it's going to be used and what it's going to be used for. So I think that those things will come. People will challenge that process a lot better as we go forward. But in terms of exactly what's going to happen, it's an open book. Launches change all the time. There's satellites that were due to launch 10 years ago that still haven't. So it's very difficult to... I mentioned earlier in the previous presentation that I used to put a slide up which showed all the future missions and then realized that most of them weren't going to get to launch. Or I'd get told afterwards that, oh, that one's not launching. So I thought it becomes very difficult to do that now because there are so many that can happen and are happening daily. It becomes very difficult to keep up to date with them. So, in summary, satellites do not have all the answers. They do, however, give us a fantastic opportunity to map very large areas at a broad scale, very small areas at a much more detailed scale, and complement absolutely all the other survey methods that we might be using day to day, and also data sets that we might also have. We can integrate together GPS data, other data sets. These all work very well together. Data is becoming cheaper. There is a lot of free data out there, which is fantastic, but it does tend to be on the lower resolution side. But that will change over time. Models are changing with some of the commercial operators where they understand that really the value is not really selling the data, it's what people can get from it. So the more they can make that data available, the more opportunities they have to collect more data, and therefore, incrementally, gain that extra revenue. So the more information we have, the better decisions we make, and the more satellites that are up there, the more redundancy we have to make as many, to bring as much of that information together as we can to help support those decisions. So with that, I will thank very much corporate members who did support. This isn't everyone, but this is everyone that I would like to thank for this particular presentation, particularly to the Institute of Environmental Analytics, who I don't think are here, but who did provide the inspiration for the talk. And with that, I will say thank you very much.
So we have time for a few questions. Gentleman there.
Thank you very much for the talk. 46 years of these satellites going up.
Yes.
And all the other satellites have gone up. It's a bit worrying that how much potential debris that is causing. And one wonders how long these satellites last. And also, the multiplicity of these satellites, can't it be reduced by having variable resolutions and including the radar aspect in the same satellite?
Good questions. Okay, so if I start with the first one, I actually had the same question in the earlier talk as well. Yes, you're quite right. There is a lot going on in space. A lot of the satellites that do become defunct, they're kind of slowly brought down out of their orbits. They typically will burn up in the atmosphere. There are a lot of satellites that are up there that don't work, that are still up there and still orbiting. But each of the orbits of the satellites that are up there are carefully planned to make sure that they don't hit something else. Because ultimately, even a tiny, tiny fleck of paint, as we saw not that long ago, can have significant damage on what is orbiting us, whether it's the ISS or, of course, one of the satellites as well. So, yes, this is something that is monitored. It is monitored quite a lot by different institutions. So there is, even though it seems like there's a kind of rush to get lots of different satellites in space, they are kind of carefully planned as well. It's not just the case that someone can just launch a satellite willy-nilly, as it were. With regards to your second question, it is a very good one, and ultimately that would be the aim going forward. The problem is really the trade-offs of the different optics and imaging requirements that would require, and to be able to balance that effectively with just on one satellite or maybe a couple of satellites with that. There are a lot of other considerations that would make that very, very difficult to combine those in that way effectively without having a very, very big satellite. And there have been satellites that have optical and radar systems on them. Very, very big means very, very expensive. So it's a trade-off. It depends who's paying for it, ultimately. So
If it's several, one larger one may be cheaper.
Possibly, but a lot of the technology that we have now means that as I mentioned, the Planet Lab satellites that we're talking about, those shoebox ones, they're about $60,000 to make. Okay, they cost a bit more to launch, but they could be launched as in bulk, a number of them together. A satellite called EnviSat that was launched in 2002, which had an optical and radar system on it, was over $1 billion. So we're talking about massive differences in scale in terms of pricing. But it's an absolutely brilliant point, and I think it is something that will change over time, but I think it might be a little while before we see technology quite pushing those boundaries in that way, but hopefully.
Thank you.
A few hands that went up here more or less simultaneously, but gentleman in the second row there first.
Okay. Yes, an ex-brother-in-law worked in the U.S. military. This is 30 years ago.
Could you use the microphone, please?
Yes. Ex-brother-in-law, U.S. military, used to brag that they could see from their satellites a 50-cent piece on the ground and tell you whether it was heads or tails. Now, I don't know if he's bragging or not, but my question is actually the military.
Yeah.
You're talking about 20, 30 centimeter. What are they down to?
Don't know. I don't know. And mainly because we don't have...
Rumor.
I wouldn't even want to stagger a guess, other than it's obviously going to be better than what we can do from commercial systems. The problem is that's also changing all the time, and they do use these satellites at 30 centimetre up to, say, 1 metre is used by the military to help support some of their military missions where they don't have maybe access to their own satellites and own systems. But I don't know how many of those are in space, and certainly don't know exact details of their resolutions, I'm afraid.
With the advent of reusable rockets coming
Yes.
in, I'm assuming that the cost of getting satellites into sustainable orbits could fall away quite quickly. And therefore, are there any obvious applications that suddenly become feasible cost effectively that until now haven't been? And can I also ask a subsidiary question? Why has the United States imposed a resolution restriction, and how do they enforce it internationally?
It's a good question. I'll answer the first one first. Yeah, the launches are becoming cheaper, and I think that will make it a lot easier to get technology into space quicker. The problem that perhaps we've had in the past is that it can take a long time to plan these missions, it can take a long time then to get the approval, then maybe to get to the launch point, and they have to be timed specifically to reach that right orbit. If we can make that process cheaper, then we've got the more opportunity to launch more. In terms of exactly the applications that has directly, it's probably more being able to get technology into space quicker than it otherwise would be. Because the problem that we've had in the past is that some of the satellites, for example, the Hyperion satellite I mentioned, that technology was already maybe 5 or 10 years out of date by the time it was launched, just because of how long that process took. Now, okay, that's a government-led mission, so there's going to be some roadblocks and delay in doing that. But if we can make that process easier, cheaper, then that does open up those doors. With regards to your second question, that's a difficult one. It's been imposed for a very long time. It impacts not just the high-resolution data. There are also some restrictions on countries as well, which are as in the limit of any satellite and what they're capable to do. That is changing, though, because they realise now that, of course, with Google Earth, in Google Earth over the United States, you can see imagery that's better than 30 centimetres because it also includes aerial data. But we're told we're not allowed to collect that data from satellites. So those things will change over time. But there's a lot of lobbying from the industry to help drive that forward. I'm sure there'll be a cut-off point for that, but I don't know what that will be. And in terms of why they have such a control, I'm not entirely sure, but that is a lot of it. I guess it's not too dissimilar to some of the sanctions that we adopt from say the US and the EU adopt similar ones. It's a similar kind of process, I believe, that's kind of impacts in terms of the resolution.
So Europe, for instance, is in agreement with this restriction on resolution?
Not necessarily in agreement, but they have to adhere to it, if you see what I mean. Yeah. So.
Thank you.
I'm conscious that there's some wine poured outside, so should we just have, I'm sure Charlotte's going to stay around for a little while, but should we just have last
Just a
question?
quick question, because you're very much part of the industry and therefore you're the user interface between the technological individuals that navel gaze and build whatever they want to, and not what you necessarily want. What satellite would you build?
Do you know what I actually had to say? It's been very similar questions as well to earlier. That is a difficult one because there are so many different things that, to me, I think would be important for geological applications. If I was to say from a Terrabotics point of view, what we would like to see is not necessarily changes in maybe the spatial and spectral resolution. I think there's obviously the more we can add to that, great, but I don't see much of that changing significantly over say the next few years at least, just because of where we are with things and technology. What for us is more important is to be able to optimize how those satellites are actually collecting data. So not the actual detail we're seeing on the ground, but from our perspective, taking a step away from the actual final end usage, but it's a more of an operational issue, I guess, is that we would like to have some more control over how those images are collected to optimize what we're seeing.
So where they fly, what the...
Not necessarily where they fly, but how they capture data. So at the moment, a satellite has the ability often to tilt in its orbit. Some of them can even flip all the way around. But they're collecting images in a very often structured way. Perhaps they have to tilt in a certain way to avoid clouds if it's an optical sensor, or optimize a collection that they otherwise wouldn't be able to catch. But from our perspective, if we're making elevation models and we have something that's a very extreme angle, it's very, very difficult for us to resolve those features and get something that's really high quality and usable. So if we can optimize those optics, even if it means that we have to wait a little bit longer, but if there was a series of those types of satellites, that would make that process a lot easier. That would be my answer.
Okay, thank you. If I can just wrap up. I am actually a geologist myself, and I remember many, many years ago working in the Andes, actually, on a mineral exploration project there, and it was very difficult terrain. It was heavily, heavily forested, and it was almost permanent cloud cover. And one day I had a radar sat image drop on my desk, and I just couldn't believe it. It seemed so counterintuitive to me that to really understand what was going on in that area, I had to go and find an image that was taken at, I don't know, 50 or 100 kilometers above the Earth's surface. I couldn't ever work that one out. It's impossible to overstate, I think, how much remotely sensed imagery has completely revolutionized the science of geology. And I certainly learned a lot more this evening about how it's being used today for environmental monitoring, cross-rail oil slicks and so on and so forth. Charlotte, you've given us an absolutely terrific story of the evolution of various satellites and the quality of the imagery that they provide, and also in terms of the applications that they're used for today. So I'm sure we'd all like to thank Charlotte once again for a fantastic talk.